So I had you go through this last night and tell me, and you wrote down a couple of things you thought were interesting. So what show us a couple of those.
So I think one of them was the graphs, which is kind of already looked at.
Well,
I guess it's the graph within the graph.
Is that on screen?
I think I have to go up a little bit.
Okay.
Yeah, so it's kind of the different how the infection passes through all of the graphs.
All right, so this is peak infected, and this is the total infected. Maybe we should, because we were just talking about total infected. Let's talk about that.
So what's kind of interesting here is that even with all these very different graphs, like even with just a plain like two-dimensional grid, just everyone linearly just has a set, like 4 people who they meet with. It always kind of has this critical area. I mean, sometimes it's a bit wider, sometimes it's a bit narrower, but they all have this critical area where suddenly they go from not infecting anyone to infecting everyone.
Yeah. So just to show you, because you hadn't seen this before, the different kinds of graphs he's using, you might think, hey, that's going to produce really different results.
Yeah.
I mean, this two-dimensional grid seems very different from these graphs.
Yeah. But when he goes and studies it, actually, very surprisingly, the behavior is very similar. On all, I don't know how well the colors show up on the screen, but if you look at the random graph or the Swat-Strogatz one or just a plain old grid, they all exhibit that same property where it suddenly transitions from the infection not spreading hardly at all to whoop, it spreads to everyone. So that's interesting.
I mean, you're setting like the value of how many people, how many like meetings, how many people you could potentially meet with. That's the same basically for every type of graph. So maybe it's not that surprising that, I mean, they look a lot different, but they're essentially the same.
Yeah, well, that's a great observation. Maybe it's less surprising than it seems. So, okay, good. So what else? What other some other things in here you thought were interesting?
I think, so this graph, I think, has to do with the density. I think here you have I'm not actually too sure it's being graphed, but I think it relates to like the density of how many people meet with how many other people.
Okay.
But what's interesting here is the behavior changes. So in total infected, you can see that at I think this is the lowest density here, you can actually stop this behavior from happening, and it just goes, because it doesn't infect the whole population, it only infects a small number of the population, which is kind of interesting.
Okay. Yeah, that's interesting. So I didn't look carefully at this part of it.
I think this is Swat-Strogatz with different density, the different densities of the graph.
Okay. Let's take a look at.
Yeah, so it's different, same distribution, different densities. So.
Oh yeah. Okay. Yep, you're right.
It's like a density of whatever the 1 to 10 is.
1 to 10 were those number of edges. Okay. So if you have a very low density of people, of connections, then the infection doesn't necessarily spread through everything.
Interesting is even slightly higher, it immediately goes back to that same behavior.
Yeah, so that's fascinating. What do you think about this?
It seems very interesting. I mean, it also shows how important it is to get this right and lower this as fast as possible. So, because if you have the lower density of the meetings, this is basically the lowest density possible, and that's the only way you can stop everyone from infecting.
Yeah, that's a good point. Well, why don't you show us one more thing you thought was interesting, and then we'll wrap up for the day.
So I think, it was kind of like this, where you move to networks of networks, and have connections between them. In this graph here, and I think there's the total version here. Shows how it's the connections between networks that spread or speed up the rate of infection.
Okay. So this was now getting to be pretty complicated, and it was actually cool that you could even generate a graph like this.
Mm-hmm.
So, this is like cities with connections in between them. And so here is the peak infection rate and the total infected rate. And it was only when each city had one connection
Between them,
this line or this jagged line, where the infection didn't spread. But like we saw in the last example, even with two connections in between, it jumped up.
Jumps.
In fact, and this is a linear plot, so even jumping from 1 to 2 was basically as much as going from 2 to 10.
Yeah. It's pretty
surprising.
neat.
So the math says you need to limit the number of connections as much as possible, and even increasing it by a little bit.
Can just nullify the whole point of limiting connections at all.
Yeah. That's cool. I thought this was one of the most well done presentations that I've seen, and it's really fascinating to me to see the math behind this and some of these results. Helps you get a good intuitive idea for how infections spread.
Yeah.
Mm-hmm.
All right. Good job this morning, guys.